No. Do you know why the camera is like this? Is live stream working? Okay, good. I mean, we can use the camera here. This makes little sense. Just use the camera over there. And then let's see. Yeah, that's better. Okay. I think there's some background issue though, as you can see. It's related to this computer. Yeah. Okay, let's get started. Everybody can hear me in the back? Good. Looks like we've lost some people. This room was more crowded in the past. You guys agree? I went for a conference and everybody's gone. Well, not everybody. You guys are still here. Okay. Today we're going to start with the architecture part of this class. And we're going to move a little bit higher up in the stack, in the transformation, levels of transformation. We're going to talk about the von Neumann model of computing and then instruction set architectures. And then we're going to bridge the gap from there to the logic later on. But just some reminders for you. Okay. There are office hours. These are hybrid, Mondays 1 to 2 p.m. There's a Moodle announcement you can check. That's correct, right? And your extra credit assignments are coming up. One is on March 21st. Some of you may have watched it. Some of you asked questions about it. Another one is coming on April 1st. So hopefully, how many people have done the extra credit assignments? At least one. Okay. Is it interesting? Okay. Okay, hopefully you'll get extra credit. Okay, so what we have learned so far, this is what we've covered. We have covered 3 weeks of lectures, plus we've started the labs. Hopefully labs are going well. I'll ask you questions later on about them. But essentially, we've started with the very high-level, device-level abstraction, transistor as a switch, and then we built logic on top of that. And we've talked about how to design that logic, both combinational and sequential, how to design finite state machines, how to describe that logic using a hardware description language so that we can actually instantiate these things at the lower level, and how to actually analyze the timing and verification functionality as well as the timing of that circuit. Does that sound good? So this is all digital design. So we are really done with the digital design part of this course. Since we don't have a lot of time in the bachelor's program in computer science here, digital design is a much bigger field, actually. You can take multiple courses on that topic, but we're dedicating 1/4 of this course to digital design. Now we're going to move up a little bit higher. We're not going to go into microarchitecture immediately because I want you to get the higher level perspective, which is really how a computer executes things. So we're going to talk about the von Neumann model, and we're going to talk about example von Neumann machines, essentially instruction set architectures that operate based on von Neumann principles, LC3 and MIPS specifically. I'm going to start with LC3, which Pat and Patel book does a great job covering the fundamentals of. And then we're going to actually give examples from 2 architectures, 2 instruction set architectures. LC3 is the Little Computer 3, which is an educational ISA. MIPS is a real ISA that's used in the field. And there are many, many other instruction set architectures like x86, ARM, RISC-V, etc., that we're not going to talk about. And then we're going to talk a little bit about assembly and programming. So we're really going to talk about programming interface to hardware today. And then later, we're going to start on microarchitecture, and we're going to have a lot of interesting microarchitectural concepts on how to implement an instruction set architecture such that you obey the software-hardware contract and do that while exploiting the logic gates that we have designed in the past. Does that sound good? Okay, so basically, we're going to build a computer. So we will learn the basic elements of a computer today, and we'll look at an example von Neumann machine. And today and tomorrow, we're going to cover instruction set architectures, including different types of instructions, operate instructions, data movement instructions, control instructions. We're going to talk about instruction formats, addressing modes, data types, etc. These are some readings. The red ones are what we're going to follow today and tomorrow, essentially. Especially Pat and Patel, I'm going to follow, but I'm going to give you examples from Harris and Harris as well. And tomorrow, we're going to talk about programming a little bit, assembly level programming. I'm sure you've seen programming in other languages, right? High level languages. And we're going to try to bridge the gap between high level language and assembly and ISA a little bit. Okay, next week, hopefully we'll start microarchitecture. We'll start implementing the ISA essentially next week. Okay, so let's jump into it. How many of you heard about the von Neumann model? Does this mean anything to you? Okay, how many people did not hear about this? It's okay, so that's good. Most people didn't hear based on the hands I've seen. Do people who have heard about it, did you hear it in classes? No? Okay, I see heads shaken, so it's probably you heard about it somewhere else. So basically, this model is really about building a computing system. I'm going to give you an alternative model, hopefully tomorrow, not today. We don't have time today. But this is not the only model, but this is really the most successful model that we've had so far because it came first partially. And it's easier to program also secondarily, I would say. Okay, so recall, I've shown you this picture before at some point. We will cover all of these components. We'll cover processing, memory, and communication, but we'll especially focus on processing initially. And for this to work, we need a model of computation. Basically, in past lectures, we learned how to design combinational logic structures, sequential logic structures. With those logic structures, we showed that you could build an ALU, arithmetic logic unit, execution units, basically. We could build a decision unit, for example. We could build memory storage units. We could build communication units. We've seen examples of this. All of these are basic elements of a computer. Today, we will raise our abstraction level to a higher level. So to this level, essentially, software-hardware interface and a little bit of microarchitecture so that you can see that software-hardware interface can be implemented in microarchitecture. But we're going to look at different implementation choices later. And we're going to use logic structures to construct this basic computing model. So what are the basic components of a computer? If you think about the fundamentals, very basics, you want to get a task done, right? We want to solve problems, as we have discussed in the first lecture. And to solve problems, we need to express those problems in a language that the computer can understand. So we need a computer program, basically, right? In the end, you write a computer program. And you have written computer programs at high-level languages. We're going to look at computer programs at a level that the machine really understands. We're going to look at ones and zeros, for example, today. What is a computer program? Computer program specifies what the computer must do, right? That's the goal. And then we need to design the computer itself so that it could carry out this program, right? To carry out that specified task that's dictated within the program that you have written. Hopefully this is obvious. You need both of these. So a program is really a set of instructions in the end. Each instruction specifies a well-defined piece of work for the computer to carry out. This is really important because we're going to have instructions that are at the level that the hardware can interpret and understand. When you write programs at a high-level language, you may write things that are very high-level, right? It could be I don't know, you make an operation on a key value store, for example. That could be part of your programming language. You do something on a hash map, right? That could be part of your programming language. Instructions the hardware itself may not understand those hash map. You need to map those things to the hardware. We're going to look at what the hardware can do, at least in the instruction sets that we're going to study. But I'm going to also show you that instruction sets can be designed to be high level as well. Okay, so what's an instruction? Instruction is really the smallest piece of specified work in a program. And these are actually all from Pat and Patel. You can read the parts that I mentioned in Pat and Patel. Instruction set is all possible instructions that a computer is designed to be able to carry out. So, okay, we're defining the instruction set right now. We're going to build up to it. But before we get to that, there should be actually a model of execution also. And that's where the von Neumann model comes in. If you want to build a computer that can carry out instructions, you need an execution model for processing programs. So John von Neumann, whose name you may have heard of in the past. How many people heard of John von Neumann? You may not know the model, but you may have heard of the name, right? He proposed, along with his colleagues, a fundamental model in 1946, which became very popular. This is what he looks like. And this is the paper. It consists of 5 components. Later, I'm going to distill 2 major things in a von Neumann model, but let's go through these 5 components first. We start with memory. Memory stores the program and the data because you need to actually have the program somewhere. You need to have the data somewhere, and you need to do something to it. Processing unit does something to it, essentially. These are the processing units. And then there is an input unit that can take input from the user, and there's an output unit that the computer can communicate with the outside world. And finally, there's a maestro, which is the control unit, which coordinates everything the computer does. It controls the order in which the instructions are carried out, essentially. So these 5 components are proposed by von Neumann. We're going to examine examples of these. And throughout this lecture, we'll examine 2 examples of the von Neumann model, the LC3, Little Computer 3, and MIPS. MIPS is a real ISA, as I said. These are good examples. These are good educational examples, but I'll give you examples from different ISAs, instruction set architectures as well. Does that sound good? Okay, cool. Okay, so I should say that all general purpose computers today use the von Neumann model. That's why we're starting with it. This doesn't mean that it may be the most efficient model. Later, for example, we're going to see accelerators for machine learning in lecture 18 or so that are based on completely different principles. They may still take instructions so that they can carry out some task, but they don't necessarily use the von Neumann model. Okay, so this is a pictorial representation of the von Neumann model. It has 5 of these components that we have discussed. We start with memory. I'm going to define some of these, and this is not magic, basically. We already built a memory, a simple one, but this was a 12-bit memory, if you remember, right? You have 4 locations here, and each location stores 3 bits. We're going to build bigger memories, and we're going to abstract it such that we can actually use instructions to specify locations. Here, this is a logic level view of memory. Right? That's a memory array. So what does the memory store in the von Neumann model? It stores both programs and data. And actually, there's no distinction between them. If you just look at memory, it's all bits. There's nothing that says, oh, this is a program and this is data. You don't distinguish between them in memory. You will distinguish between them when you're processing, when you're actually executing instructions, as we will see. So control logic, that control unit distinguishes, treats a particular memory location, memory address, as containing an instruction versus data, depending on when it accesses it. This will become more clear. Okay, memory contains bits, as I said. Bits are logically grouped. They could be logically grouped into bytes. And in these ISAs that we're going to look at, instructions architectures that we're going to look at, they're grouped into bytes. A byte is 8 bits. These are actually terminology that comes from 1960s, from IBM 369091, which is one of the very interesting computers. And words. Word could be actually 8, 16, or 32 bits, depending on the instruction set architecture. So we have actually defined some of these things earlier. Address space is the total number of uniquely identifiable locations in memory. In LC3, for example, the address space is 2 to the 16, meaning you have 16-bit addresses, okay? In MIPS, the address space happens to be 2 to the 32, 32-bit addresses. In a more like a modern ISA, instruction set architecture, x86-64, the address space is up to 2 to the 48, meaning you can have 48-bit addresses. So your memories that can be, this address space is what could be referenced by the programs. A program can reference very large amounts of memory if you're given this address space. Okay, addressability is how many bits are stored in each location, meaning in each address. For example, you can be 8-bit addressable. In other words, byte addressable. Many ISAs today are byte addressable. Or you could be word addressable, meaning your address can specify 32 bits, for example, assuming your word is 32 bits. In LC3, for example, a word is 16 bits, and your word addressable. These will become also more clear. But these are some definitions, and these are the things that the programmer sees. Whenever you program at a low level as an assembly programmer that looks at the instruction set of a computer, you see the address space. This address space is specified in the ISA document. You see the addressability so that you know what an instruction is going to do, how big the address will be, and how much data that you can specify with a single address, 8-bit or a single word. And we will see that there are different instructions that could be referring to a single word or a single byte. So that we can, for example, get a single byte from memory or get a whole word from memory. Okay, I just said this basically. A given instruction can operate on a byte or a word, and we will see examples of this, hopefully by the end of this lecture. Okay, this is a simple example, a representation of memory with 8 locations. You have the addresses of these locations. Since there are 8 locations, you have 3 bits to identify each location. We should be able to do these calculations very easily by now. And each location happens to contain 8 bits, 1 byte over here. So you can think of this as byte addressable memory, and the address space is 8. Okay, each location has 8 bits. So this is an example from Pat and Patel also. If you look at this, value 6 is stored in address 4. Address 4 is this, and value 6 is stored there, and value 4 is stored in address 6. Just to confuse you. It's not confusion, of course. You know how to deal with your bits probably, right? Okay, so one question is, let's make, this is one specification of the ISA, for example. You can say, my address space is this big, and my addressability is 8 bits, and this is what I have. You could design an ISA this way, but this is very limiting, clearly. You don't want memories that are this small, so modern ISAs are much larger, as we discussed in the earlier slide. But just for fun, if I ask you the question, how can we make the same size memory bits addressable? What this would do is essentially the size of this memory is total 8 locations, 8 bits each, 64 bits. If it's bit addressable, you would have 64 locations where each location is a single bit, right? So your address size would be 6 bits, and each location would specify 1 bit. So it's possible to do that. Most computers today are not programmed that way. You don't have instructions that operate on bits. The granularity at which you can get data from memory is usually, the smallest is 8 bits, meaning 1 byte. This is changing with machine learning a little bit, because people are figuring out that sometimes actually you want to use smaller data types. I'm going to define the data type later on, like 1 bit, 2 bit, 4 bits, so that you can operate on smaller data elements, because it turns out operating on larger data elements is expensive in terms of energy and computation power. If you operate on smaller data elements, you can actually be much more energy efficient. So things may be changing as ISAs and workloads evolve into the future, and the energy requirements push people to do something different. So it's good to basically know that you can go into trade-offs like this. Okay, so let's talk about word addressable memory. Word addressable memory says that each data word has a unique address. If it was bit addressable, each data bit would have a unique address. Let's start with word addressable. In MIPS, for example, a unique address, you have a unique address for each 32-bit data word. In LC3, this is specified by the ISA designer. Somebody designs this hardware-software interface, somebody documents it. It's like a contract, 4,000-page contract, as you will see later, today, tomorrow probably, where they specify everything that the programmer, some programmer needs to know in terms of how to program this hardware, right? In LC3, somebody specified that a unique address, there should be a unique address for each 16-bit data word. Okay, so let's take a look at MIPS memory. MIPS memory looks like this, basically. So at the bottom, you see word 0, and then you have word 1, and then you have word 2, and then you have word 3, and these are some random data that we have, right? And here we have hexadecimal representation. You have 4 bits here, and you have 8 of these 4 bits, so you have 32 bits total, right? Hopefully it makes sense. Okay, so you have a word address, essentially. This is word address 0, word address 1, word address 2, word address 3. If you specify, oh, I want to get the data at word address 3, you will have an instruction that enables you to express that to the computer, and the computer will access this memory location because it's address 3 using a decoder, if you remember. And that data will be transferred somewhere, as we will see soon, and you will get this data, okay? Okay, let's take a look at byte addressable memory. In this case, each byte has a unique address. MIPS actually is byte addressable, it turns out. LC3 is not byte addressable, but there's an updated version of LC3, Little Computer 3B, that says byte addressable as well. So now this is our MIPS memory that became byte addressable. I didn't show you the longer version, but I actually divided the words into 4 pieces over here. Each of them is a byte, as you can see. And this is the byte address now. So you can see that we don't have a word address. Here, we have a byte address 0, and one of them is 0 over here. We're going to talk about that soon. So let's assume that this is 0. This is byte address 0, byte address 1, byte address 2, byte address 3. And then, you have byte address 4 over here. This is 4, 5, 6, 7, 8, 9, 10, 11, etc. Right? You can do it hexadecimal. Okay, so now we're byte addressable. Whenever we use an instruction that says, oh, get this byte for me, let's say I want byte 4. And you somehow specify the address, and we will see all of that. We will see how we specify all of those to the computer. If you say, I want byte address 4 using an instruction, the computer will get you F7, assuming some ordering, as we will see. Okay? So this all clearly brings up the question, how are these 4 bytes ordered? So people actually think some data is expressed in terms of bytes, some data is expressed in terms of words, right? You may have a large data type, like 32 bits, but your memory may be byte addressable, meaning it consists of 8 bits each. Then if you think about a word, how do you actually lay out the word matters. So how are these 4 bytes ordered becomes a question. I'm going to quickly divulge into that. But basically, the question is, which of these 4 bytes is the most versus least significant? Right? Is the most significant byte here, or is it here? Okay. So you may have read Gulliver's Travels. How many people read Gulliver's Travels at some point? Not at school. They don't teach this at school anymore. Not for fun. You know, there might be more fun things these days. I don't know. But I would recommend reading this. These are beautiful stories. But basically, Gulliver encounters folks that are big endian versus little endian. And this has influenced computer terminology also. And these folks are different folks. They're different in the way they break their eggs. You know, eggs look like this, right? They're asymmetric. They're not symmetric in general. And some folks decide to break their eggs on this side, the big side. They're called big endian. And some other folks decide to break their eggs on the left side, the little side. They're called little endian. Make sense? Why do they do it this way? Because they're used to doing it that way, right? If you're born to a place where everybody starts breaking their eggs on the big part, then you keep doing that probably. Well, you could start a new trend, of course, over there, but you may not be immediately accepted at that place. So this is a convention, basically, or tradition, in other words. So which one is better? Neither of them, maybe. I mean, depends on your taste, perhaps, right? So basically, we have a similar issue over here. If you look at the memory that we have designed, and now these are not data over here, these are the addresses, byte addresses I have put for each word. Word addresses are the same. In a big endian machine, you lay out the words such that the most significant byte of a word is at the lower address. So if you specify address 0, you get the most significant byte in that word that you store. If you specify address 3, you get the least significant byte, right? Why does this matter? Because if you have a 32-bit value and if you want to add it to another value, you want to know what's the most significant bit and what's the least significant bit, right? Because these are very different things. Bit 0 affects the addition the least because it's the least significant bit. Bit 31 affects the addition the most because it's the most significant bit, right? Okay, in the little endian world, it turns out least significant byte is in a word is at the lower address, like this, and most significant byte is at a higher address. Again, you can say, oh, okay, this is more intuitive for me. Maybe, because it's least and the address is lower. I get that. But in the end, you could be living in a world where this is the norm for you. And it's certainly possible to do that, right? You just need to rewire your thinking. And if you're always rewired that way, this is more natural to you than this. No question about that, right? So basically, this is a convention. Does this really matter? In the end, if you know where to put your least significant bytes, it doesn't matter. Where it really matters is when one big endian system communicates with a little endian system and they need to talk to each other. So you have a computer that lays out the data in one way because it's in one ISA that is big endian, and you have another computer of the network that uses the little endian convention. When they need to communicate with each other, they somehow need to make sure that the least significant byte in one computer stays the least significant byte in the other computer, right? Basically, they need to do some reordering. Okay, this is good to know. And it's also, this actually has a lot of lessons that I don't want to go into, but convention actually affects a lot of the designs that we have. Okay, so how do you access memory? That is a logical view of memory that we have, least significant bytes, most significant bytes, etc. Now let's talk about accessing memory. So there are two ways of accessing memory. You need to read or load data from a memory location, and you need to write or store data into a memory location, okay? So these are the higher level things. And then internally, we're going to use two things, memory address register and memory data register, to facilitate this access. This is one implementation. There could be multiple implementations, but now we're actually blurring the line between abstraction level of programming and implementation. There's a memory address register in the von Neumann model, and then there's a memory data register. To read, you first load the memory address register with the address we wish to read from. It could be a 16-bit address, for example. And in the second step, data in the corresponding location gets placed in the memory data register using some circuitry in the memory, okay? We're gonna demystify that circuitry later. To write, there are two steps also. One, the first step is you load the MAR, memory address register, with the address, and MDR with the data we wish to write, because we're going to write that data to that address. And you activate the write enable signal into memory, which ensures that the value in MDR is written to the address specified by MAR. Make sense? Okay, this is one way of implementation, and this is perhaps the simplest way of thinking about memory. Okay, so we've covered the memory right now. That's the memory part of the von Neumann model. Let's talk about the processing unit. Processing unit looks interesting because it has one component that we have seen, ALU. Hopefully people remember ALU. Do people remember ALU from last, not the last, previous lectures? Okay, good. But you probably don't know what temp is. Temp is an important thing, and it's going to introduce some concepts that are going to appear again and again and again and again in our lectures, which is locality, and we're going to build a memory hierarchy out of that temp later. Okay, so processing unit. The main function of a processing unit is to perform actual computations. This is what a computer is designed to do, right? Add, multiply and accumulate, convolution. It could be any operation, XOR. The processing unit can consist of many functional units. And we started with an arithmetic logic unit in the past. It executes computation and logic operations. In LC3, there are only 4 operations. Well, add, and not. Actually, there are 3 operations. There was an XOR added later on. In MIPS, there are a bunch of these operations. You will see these later on. So there's a NOR, keep that in mind, because there will be a question later on that will relate to NOR. But there are other things like multiply also. There's a story about multiply that I'm not going to tell right now, but there are interesting stories over here. So the ALU processes quantities that are referred to as words. So they operate on words in general, but they could operate, an ALU can also operate on bytes. In LC3, the word length is 16 bits. In MIPS, the word length is 32 bits. This is the maximum operation length of an ALU. Okay, so recall this is the ALU that we designed in a past lecture. I will not go through this, but this is to jog your memory. So this is, again, not magic. We know how to design this thing, at least a subset of the MIPS ISA. Okay, so what else is there in the processing unit? This is an important concept. It's not just about processing. Usually, well, essentially, when you do processing, you operate on data, right? Where does the data come from? Yes, it comes from memory. But you need memory close to the processing unit as well, because memory far away is too far away. And this is called the fast temporary storage. It's almost always the case that a computer provides this fast temporary storage, essentially a small amount of storage very close to ALU. And this is visible to the programmer. So we're going to actually explicitly specify the storage separately from the memory. You can think of this as a small amount of memory close to the ALU. The purpose is to store temporary values and quickly access them later. This is how fundamental data access and memory is to our instruction set architectures. Okay, so for example, I'm going to do this calculation, A plus B times C divided by D in that order. You have intermediate results, right? Your intermediate result of A plus B, if you do an add, A plus B, you can store it in the temporary storage as opposed to writing it back to memory. Because it's too slow to store each ALU result in memory and then retrieve it again for future use. If you had some small temporary storage, small amount of memory, very close, you could do this very quickly. As we have discussed in earlier lectures, a memory access is much slower than an addition, multiplication, or division. That's the key over here. That's true for the intermediate result of A plus B times C. You did an add operation to do this, and then you did a multiply. Where do you store the results? You store it in a temporary storage. We're going to call these registers soon. Yes, basically this temporary storage is usually a set of registers. It's also called a register file. It's essentially a small amount of memory that is addressable by the instructions so that you can store these temporary results, so that you don't need to go to main memory to access things. So basically we have fast temporary storage. Let me motivate it again over here, because this is going to appear again and again later on. Memory is large, but slow. Memory, what do I mean by memory? Memory is this. Well, let's go back. This is memory. This thing over here is large, but slow. In x86, it's 48 bits, 2 to the 48, 8-bit elements, right? We don't want to go there all the time. So we have registers in the processing unit. They ensure fast access to values to be processed in the ALU. Typically, one register contains one word, same as word length, because you operate on words in an ALU. So this is called a register set or register file. It's visible to the programmer. It's part of the instruction set architecture, separate from memory. It's essentially a set of registers that can be manipulated by instructions. LC3, for example, has 8 general purpose registers. And they're numbered R0 through R7. Because you have 8, you need 3 bits to specify a register. So you can think of this as a small memory that is essentially that has 8 locations, where each location stores a word. Register size, word length, as I said. MIPS has 32 general purpose registers, as you will see in your programs. It gives you bigger, fast temporary storage. And again, they're specified from R0 through R31. So you have a 5-bit register ID or register number, which requires more space in your instruction. As a result, your instructions need to be larger in MIPS. Your instructions are actually smaller in LC3. And register size is larger in MIPS because MIPS word length is 32 bits, as we have discussed. Okay, so now we've introduced registers. We're going to do a lot of programming on registers later on today, and also later in this course. Hopefully this makes sense. Okay, recall this is not also magic. We have built this register. We call this register. So this is a 4-bit register if you look at this. It could be a 30, you can imagine a 32-bit register also, right? Okay. So this is another example of this 4-bit register. So these are mnemonics that I'm not going to go through, but these are some conventions in terms of how registers are named in MIPS. It's really R0 through R31, but at the higher level, when you program, you may refer to registers like this, and the compiler can compile it into these numbers. Okay, we may get back to this when we do assembly program. Okay, so we've covered memory and the processing unit. Let's talk about input and output quickly. We're not going to talk about that in detail yet, but these are critical also. They enable information to get into and out of a computer, clearly. You can use many devices for input and output. These are also called peripherals. Input can be keyboard, mouse, scanner, disks, etc., many things. Output can be the monitor, printer, disks, etc. So today, actually, we have many more input and output devices potentially. In LC3, as you will see in Pat and Patel book, they consider a keyboard and a monitor, and they have special locations in memory to access them. We will not talk about this right now. We may get back to it later. But let's talk about the control unit, which really orchestrates how all of these are put together. It's essentially like the conductor of an orchestra, right? You have orchestra, they're all doing different things, and the conductor really conducts who should be doing what at what point in time. Essentially, the control unit conducts a step-by-step process of executing every instruction in a program in sequence. And we're going to see that today. It keeps track of which instruction is being processed via this register called PC, instruction register. Instruction register is actually the bits of the instruction that you're currently processing. It contains essentially it contains the instruction word, if you will. And we will see that. We will see different instruction words soon. And then this instruction register gets interpreted by the processor, where the processor figures out, oh, this instruction specifies that I should do an add, right? This other instruction specifies that I should do a load. But you have one instruction at a time in this instruction register. It also keeps track of which instruction to process next via program counter. This program counter or instruction pointer, it's another register that contains the address of the next instruction to process. Does that make sense? So you basically start with a program counter, fetch an instruction, put it in the instruction register, and then increment the program counter. Once the current instruction finishes processing, you fetch the next instruction from the incremented program counter, put it into the instruction register, process that instruction, increment the program counter, and then once this instruction is done, you remove it from the instruction register or fetch the next instruction into the instruction register. And you keep incrementing the program counter so that you can go to the next instruction in a sequential manner. And instruction register provides the storage for the bits of the instruction that specify what the computer should do. So program counter is the address to fetch the next instruction from. Instruction register is the data value of the instruction. Does that make sense? Okay. So basically, we've kind of built our architectural state. I didn't tell you exactly, but these are all visible to the programmer except for the instruction register. These are the things that are visible to the programmer. When you program, instruction set architecture exposes to the programmer memory, which is essentially an array of storage locations indexed by an address. You have addressability, address size, etc. And you have registers, general purpose registers. These are given special names in the ISA as opposed to addresses. Fast temporary storage, as we have discussed. There could be also special purpose registers, which we're not going to deal with yet. And then there's a program counter. This is the memory address of either the current or the next instruction, depending on where you are in the instruction processing cycle, which we will get to soon. These are three key parts in a machine that are visible to the programmer. And instructions, programs are a set of instructions, specify how to transform the values of this programmer visible state. For example, an add instruction says, add this register to this other register and put the result into this destination register. Basically, add instruction operates on two registers. A load instruction will load a value from a memory location, load from this address in memory into this register. And then you may have a store instruction that says, take the data value in this register and store it into this memory location. So all of the instructions that we will see will operate on these entities, which are visible to the programmer. That's why this is so important, and that's why I'm spending a lot of time on this slide. This is the architectural state, visible to the programmer. We will also see instructions that operate on the program counter. Actually, all instructions operate on the program counter. Whenever you fetch an instruction, execute it, you go to the next instruction. You increment the program counter, in other words. But then we're going to do more sophisticated things to the program counter, because executing sequentially in a program is not that useful, right? Sometimes you want to do something else in a program based on some data value. For example, you say, if this data value is greater than 5, I execute this code. If this data value is smaller than 5, I execute this other code, right? So you do some conditional action. And if all you're doing in a program is actually going sequentially by incrementing the program counter, you don't have that. So we'll introduce branches or control flow into the program that take the program counter, change it to a value, which will take you to the right place in the program. Does that make sense? If you want to execute a function call, for example, you program with functions. I want to call this function that requires changing the program counter to the value, to the address of the function, essentially. And function is essentially a set of instructions in memory somewhere that you can jump to by changing the program counter. Okay, so we've covered the von Neumann model, at least at some basic level. Let me give you two other properties of the von Neumann model that I kind of implicitly suggested. It's also called a stored program computer. Instructions are in memory, essentially. It has two key properties. One is stored program. I'm going to define it a little bit nicer. And the second is sequential instruction processing, which I kind of harped on earlier. So essentially, stored program means instructions are stored in memory in a linear array. Memory is unified between instructions and data. So there's no distinction, basically, in memory between instructions and data. The interpretation of a stored value depends on the control signals. Whenever the processor is actually accessing memory, in what part of the instruction cycle, as we will see soon. Okay, this may be difficult to understand right now, but it'll become clear soon, hopefully. Let's talk about sequential instruction processing. This is easier to understand. You basically have one instruction processed, fetched, executed, completed at a given time. Program counter, instruction pointer identifies the current instruction, or when it's incremented, the next instruction. And this program counter is advanced sequentially by being incremented, except for control transfer instructions, which are branches or jumps, as we will see. But it's very sequential. And this is part of the success of the von Neumann model. Whenever you write a program, you write a sequence of commands, and you expect that one instruction in the sequence is executed first before you go to the next instruction, And this enables a lot of things like easy debugging, easy thinking about how things are performed. Yes?
Why is memory slower than the registers for temporary data?
Because large is slow. If you have large memory, let's say 2 to the 48 locations, imagine, based on what we have discussed earlier in earlier lectures, how big of a decoder do you need? How big of a multiplexer do you need? How big of an array do you need? Like all of them are larger, and based on the timing and verification lectures, that requires a huge amount of combinational logic. The delay is much larger, right? If you have only 8 registers, your decoder is much smaller, your multiplexer is much smaller, your array is much smaller, so your access times are much slower. Okay, very good question because there's no magic. Basically, we built up to all of these, right? Yes?
How do we decide which goes back into the memory and which gets stored?
That's a great question. I'm not going to answer that question. Meaning, that's an important question. What is stored in the registers versus what do you put into memory? That's the job of a good programmer, essentially. Everything can be in memory. You decide not to use the registers, your program will be terribly slow. Today's compilers do register allocation. Essentially, what today's compilers do, they do some locality analysis in your program. They try to figure out automatically which variables should be stored in the registers next to the processing unit, and they do the register allocation. If you're programming with a nice high-level language, with a nice compiler, etc. If you're programming in assembly, you're on your own. You'd better do the register allocation yourself. Make sense? Very good question, too. These issues will come up in the memory hierarchy again and again. What goes into the cache? What goes into the other cache? What goes into the other cache? Who brings the data from one cache to another cache? Right? We're going to see that in lectures 20 plus. But we're getting there. But we just introduced the registers. Okay, so these are the 2 key characteristics of the von Neumann model that you should never forget. Okay, now let's go start building a von Neumann machine. And I'm going to start with LC3 because this is easier, I think, and your book, Pat and Patel book, does a great job explaining how this operates. I think for this part of the discussion, I would definitely recommend the Pat and Patel book. Okay, so this is another von Neumann machine. A lot of components are von Neumann. And basically what we have is all von Neumann machines today. This is the LC3 von Neumann machine. And you can identify different parts. This is the control unit. These are the control signals. This is just to acclimate you with what is coming next. We have data. Data is marked with black edged arrows over here. Control is usually marked with white edged arrows so that you can distinguish between control signals and data. This is memory, 16-bit addressable. And you can see the MAR and MDR over here. Memory address register and memory data register. You have a keyboard and you have a monitor. You have different registers for those that we're not going to go into, but you can read in the book. There's an ALU, 2 inputs, 1 output. There's a register file, fast temporary storage, 8 general purpose registers. You have 2 registers you can read concurrently from the register file. There's an instruction register, as we have discussed. This stores the current instruction that's being processed. There is a program counter. It stores the address of either the current instruction or the next instruction, depending on where you are in the instruction cycle. There is the finite state machine that generates the control signals, that takes input, that takes as input the instruction register. It looks at the bits on the instruction. It says, oh, I need to orchestrate things such that this add is done, right? And we're going to see some of that. There's a clock. This is a synchronous machine, as we have discussed in the past. And this control signals, one of the control signals that's generated is the ALU operation. What should the ALU do to process this instruction, right? And then there's another thing, the tri-state buffer, if you remember tri-state buffers from the combinational logic lecture. This tri-state buffer is used to place the result coming out of the ALU onto this huge thing called the system bus, processor bus in this case, so that the result of the ALU can be potentially put to memory, for example, right? Or can be potentially put to the register file. Okay, and then there's a signal coming from the control unit that controls the tri-state buffer, so that if you generate the control signal at the right time, when the result is generated, and you put the result somewhere else. We're going to see all of these soon, and that's the processor bus. Okay, so we're going to build up to this machine, but I'm going to give you examples first on how the instructions are processed. Okay, we've already discussed this. Instructions and data are stored in memory. Typically, the instruction length is the word length. The processor fetches instructions from memory sequentially. It fetches one instruction, decodes and executes the instruction, continues with the next instruction after that. So the address of the current instruction is stored in the program counter, and then you increment it at some point while the instruction is being processed. If you have a word addressable memory, the processor increments the program counter by 1, because instruction is 1 word, and then you keep incrementing the program counter. If you have byte addressable memory, the processor increments the program counter by the instruction length in bytes. We're going to see by 4, because your addresses are referring to 1 byte, And each instruction is 4 bytes. So if you want to go to the next instruction, you increment the address by 4, right? As opposed to by 1. So there are some interactions with the operating system also that we're not right now going to talk about, but there should be a way for the system software to say, oh, start this program to the machine. We're not going to talk about those interactions yet. The system is actually more complicated than what we're going to look at today. But for the operating system, for example, when it starts the machine, when it sets up the machine, after the machine is reset, it points the program counter to a particular location. In this case, that particular address that MIPS designers decided to say. That's where the program should start, basically. Let me give you this, and then we're going to take a break. So this is a sample MIPS program. You have 4 instructions stored in consecutive words in memory. It's essentially assembly code. So if you take the MIPS ISA would specify what these are to you. This is a load instruction, this is an add instruction, this is an add immediate instruction, this is a subtract instruction. Hopefully we're going to see a lot of these. There's no need to understand this program now. We will get back to it. But this program is not what the machine sees. What the machine sees is this, encoded instructions. So there needs to be a way of encoding this, because this is not what you store in memory, right? In the memory that we design, we store bits, zeros and ones. There's no L, there's no W, there's no T2, there's no any of that, right? There's an encoding that needs to happen such that in memory, we have the sequential set of instructions. Make sense? So the instruction set architecture, that 4,000-page book, in part, specifies what that encoding is. If you want to specify a load word or an add, if you prefer, okay, then you encode it this way. So we're going to see that encoding in the later part of this lecture. And this is important. So someone needs to do that encoding. In the past, humans did that encoding. Today, compilers do that encoding, right? Because this is actually easily automated. In memory, this is what you see. This is what MIPS memory looks like. These are the instructions. And lower is lower address in this particular case. I show you byte addresses over here. So you can see that the first instruction is at this address for blah, blah, blah. The next instruction is that address plus 4. The next instruction is that address plus 8. The next instruction address plus 4, plus 4 from the previous one, essentially. And you can see this is what we store in memory. Each of them is 4 bits, and you have 8 of these 4 bits, 32-bit instructions. Initially, the program counter is set here, and the machine fetches this instruction, puts it in the instruction register, and executes it. Once it's done, the machine goes to the next program counter, meaning increments the program counter, and fetches this instruction, puts it into the instruction register, decodes it, and executes it. And it keeps doing that, essentially. Okay, this is a good time to take a break. Let's be back when the bell rings, and then we're going to see this instruction processing cycle, and then we're going to see the entire ISA, hopefully, soon.
Wir müssen das nächste noch haben.
Das ist Tab 1. Tab 1 ist Release.
Ja, aber das wird vorstellen. Ich zeig dir. Tab 1, da kannst du gar nichts abgeben. Das ist nur die Note, die wir gegeben haben. Für nächste Woche ist Tab. Aber wir können es trotzdem byte abgeben.
Ja. Danke, das Wort. Aber das.
Aber für 55 Minuten.
Ja, das habe ich schon gemacht. Es sei denn, ich glaube, sollte man ein Matchen mit einer Lösung dass man aus Skip-Daten bestimmte auslösen kann. Aber das ist ein bisschen anders.
Ich habe 36, ja. Das weiß ich, das hat die Matteo gedrückt.
Wieso?
August ist 25. Ja, wir können die zum Erben von 5 Bilden, ja, 4. Ja, es ist wirklich ungünstig. Wir haben sehr viel. Jede mögliche Kombination. Ohne die Reihenfolge zu. Ja. Und B ist jede mögliche Reihenfolge. Also das linke ist hat Ufer. Nein, doch. Also 52 mal 51 bis mal 48 durch 5 Fakultätsknoten. An der linken Seite und 25 mal umgekehrt. 52 mal 51 mal 50 mal 49 auf der rechten Seite. Und ja. Und an der linken Seite haben wir Fakultät gleich 120 hier, ja, 48 Möglichkeiten für die 15 Charaktere. Ja. Also es gibt einfach okay, ich weiß nicht, was möglich ist. Ich weiß nicht, wie.
A ist jede 52 Schuster und E ist jede Nation von 48 Teilen oder 42 Teilen.
42. Aber wir haben 48 Möglichkeiten für die 5 Karten mit hier schon.
Dann, okay. Und wie viele Variante gibt es von jedem Mutlu?
Aus 120 und das die 48.
Was bedeutet dann am Ende des Monats?
Dass das möglich ist. Also von dieser
und wieso entscheidet ihr das wirklich
das nicht wirklich, also sie haben
der Kurs von heute wird wirklich sein.
Ich lerne sowieso nicht so. Kennt jemand das Passwort für IEDM? Sowas. Welche E-Mail-Adresse und so?
Das ist eine entweder Ruhe oder was?
Ja.
Und zweite Passwort. Man sollte am Anfang hat man zwei Passwörter.
Okay. Okay, let's get started for the second part of the lecture. This was a slide where we finished. Now we're going to talk about instructions, and we're going to get to the details of each of these instructions that may be of interest. And we're going to talk about the instruction processing cycle. And we're going to map these instructions a little bit into this picture that I showed you earlier of the von Neumann machine. I should say that this is one particular implementation or microarchitecture that implements the LC3 ISA. We're going to go a lot more into depth of this and some other microarchitectures later on, but this is one way of implementing things. This is not the only way. There could be thousands of different ways of implementing things. This is a nice and clean way that is relatively simple. We're going to get to different ways of implementing later on. That'll start next week. Okay, now let's talk about these instructions. Essentially, instruction is the most basic unit of computer processing. Instructions are the words in the language of a computer. Hardware understands these instructions. Instruction set architecture is really the vocabulary of that language. So you could imagine different ways of designing this, right? Like any other computer language or human language, there are many different ways of communicating information, right? The language of the computer can be written as machine language. This is the computer readable representation, ones and zeros, which is basically what I showed you over here. These are not ones and zeros, but they're grouped into 4 bits each. This is the hexadecimal notation, right? They're basically grouped ones and zeros. And then there's the assembly language, which is the human readable representation, which is essentially something that looks like this, right? Well, not as human readable as a higher level language is, right? You could actually become more and more human readable, right? And at some point, you don't need to read also, you just speak, and then things get translated into these things, right? Today, we're at a point where that is possible, except maybe that's not perfectly good at this point yet. Okay, so think about that. So we will study LC3 instructions and MIPS instructions. It's good to study different instructions and architectures because fundamental principles are similar, but I don't want you to take away with just one ISA. It's good to know different ways of doing things because by contrasting some simple differences, you can really understand the trade-offs much better. If you just studied one architecture, then you may not be able to see some of the trade-offs that I would like to highlight. A lot of things will be similar though. Principles are essentially similar on other ISAs as well, like x86, ARM, RISC-V, which are the dominant ISAs that exist today. Okay, so instruction is made up of 2 parts, opcode and operands. This is very fundamental. What is an opcode? An opcode essentially specifies what the instruction does or should do. Operation code, in other words. Operands specify who the instruction is to do it to. Basically, what are we operating on, right? Both are specified in the instruction format or instruction encoding, and we're going to see that specification. For example, an LC3 instruction encoding consists of 16 bits. That's the word size in LC3. Each bit means something, as we will see. So this is one example. This is a 16-bit representation. This is the opcode. 0001 is the opcode for an add. How do I know that? I look at the LC3B ISA manual. It says that, or LC3 ISA manual. It says that if I want to write add in machine code, I should have the top 4 bits opcode be 0001. That way, some hardware designer can design hardware that decodes that. And once you use a decoder, a 4 to 16 decoder, you'll figure out what instruction that is, right? So we have built these components. And then the next 3 bits specify a register. The next 3 bits specify another register. The next 3 bits should be 0. And the next 3 bits specify another register. So this is one instruction in LC3, and we will see why it looks this way. So basically, opcode is specified as the top 4 bits. And there are 16 distinct opcodes in LC3, because 4 bits, you can specify 2 to the 4 distinct values, right? We know this is bread and butter for you right now. And if you want to decode this, you use a decoder. That's also hopefully becoming bread and butter for you. Bits 11 and 0 are used to figure out where the operands are, the remaining bits. And we're going to call these addressing modes. Basically, how do you figure out where your operands are, where your source registers are, where your destination registers are? In this particular case, this add specifies, because these 4 bits are add, you're going to do an add. It turns out, because this bit is 0, these 3 bits are interpreted as a source register. We'll get back to that. If this bit was 1, these 5 bits would be interpreted as an immediate value over there, as opposed to a register. So this is one of your source registers, this is another source register, and this is a destination register. So this encoding specifies that we should do an add, and we should add the value in R6 to R2 and store the result in R6. These are general purpose registers. So this encoding specifies that. You just need to build the machine, build the logic that does it. And we're going to build up to that. And we're going to give you the key parts today. Okay, so that was an add. But there are different instruction types. And there are 3 main types of instructions. Operate instructions, execute operations in the ALU. Data movement instructions, read from or write to memory. Also implicit in operate instructions use registers. Because registers are a critical component of the this ALU, next to ALU, right? Okay, control flow instructions change the sequence of execution. Hopefully we're going to look at all of them today, but we're going to go into more detail. So let's start with some example instructions. This is an example operate instruction, right? High-level code. This is not an instruction yet. A equals B plus C. You could use your favorite programming language, declare your variables. You can say A equals B plus C, right? It's possible to do that. Assembly could be like this. In this case, add A, B, C. A is the destination. B is one operand. C is another operand. This is not exactly low-level assembly because it doesn't have the register allocation done yet. These are variables, A, B, C. Add is called a mnemonic to indicate the operation to perform. B and C are source operands, and A is the destination operand. So that's the semantic specification of this assembly, right? Now you need to map the variables to registers. So this is the assembly. In LC3, somebody needs to do that register allocation. Human can do it, compiler can do it. Let's do it as humans. And as human, I decide B should be register 1, C should be register 2, A should be register 0. MIPS has a different way of specifying registers, but it's essentially the same. S1, S2, S0. Okay? So now we map the variables to registers. This is what an LC3 instruction looks like after you do the register mapping to the variables. Add R0, R1, R2. R0 is the destination. Destination, depending on the convention, destination can be on the left, destination can be on the right, but our convention is destination is on the left. So let's look at the field values. If you want to specify this, you go to the manual, and the manual says an add opcode is 1, and we're adding 2 registers, so this should be 0, and these 2 should be zeros also. I don't know how strict the manual was on that, but that's how it is. And this is source register 2, it's 2. This is source register 1, which is 1. This is destination register 0. So if you look at the instruction encoding, these are exactly what 16 bits are. So each bit you can specify. That's the machine code essentially. Right? It's essentially what I said over here, where each bit is put into its place. So this is our encoding. You can also write this in hexadecimal. So you write this in hexadecimal, put it in memory. When the program counter gets to it, that instruction gets executed. When the program counter is the address of the instruction to execute, if you remember earlier things that I said. Essentially, this instruction specifies that an addition should be done on register 1 and register 2, and the result should be stored in register 0. Okay, I'm going through this relatively slowly because we're going to do more of these soon. So that was our instruction format, basically. This is our instruction format and encoding. LC3 operate instruction format is actually very general. You have an opcode, 4 bits in the top 4 bits, bits 15 through 12. These are the most significant bits. And then you have the destination register and then the source register. These 3 bits are always set to 0. And then you have the second source register over here. So op is opcode, what the instruction does or should do. For example, add opcode happens to be 0001 because whoever designed the LC3 ISA said that should be so. And opcode is actually 0101. Okay. SR1 and SR2 are source registers, DR is the destination register. Okay. So the semantics of add is DR gets the value of SR1 plus SR2. Basically, the data value in SR1 gets added to a data value in SR2. The result gets stored into a destination register, okay, DR. Semantics of AND is very similar. It's not add, it's essentially an AND, logical, bitwise AND operation, okay? And this is one example. We actually looked at this. In this case, you do an add R2 plus R6, and the result goes to R6. So source and destination register can be the same, right? You can overwrite the source register after you produce the result. Okay, so this is add in MIPS. It's going to be very similar. You add S1 to S2 and store the result in S0. These are the field values. They look a little bit longer. I'm going to look at the machine code directly. What this does is basically RD, destination register specified over here, gets RS plus RT. In this case, you basically, it turns out S0, S1, and S2 are 16, 17, and 18. There's a mapping also over there that is done. But don't worry about that right now. This thing specifies that you should add RS, register 17, to register 18, and store the result in register 16. Okay, this is the machine code, the instruction encoding. Opcode is 0. This funct is actually very important because it's an extended opcode. So in MIPS, things are a little bit more complicated, as you can see. Instructions are 32 bits, longer. There are more general purpose registers, so you need more bits to specify them, 5 bits each. So you need 15 bits to specify 2 source registers and 1 destination register. And your opcode is, as you can see, 6 bits. And then there's function, that's also 6 bits. It turns out that's an extended opcode. You need more operations than a real ISA. Okay, and that's the encoding. Okay, and this is the R-type instruction format. So you have 3 register operands. 0 is the opcode. RS and RT are the source registers. That's where they're placed in the encoding because somebody decided that it should be so. RD is the destination register. Shamped, you don't need to worry about that. It's a shift amount only for shift operations. You may see that later on. Funct is very important. This is operation R-type instructions. Basically, R-type instructions are operate instructions with register values. They operate on registers. 0 is always the opcode. Funct is the extended opcode. It tells you what really you should do. 0 doesn't mean anything in a sense. 0 means you should do something to these registers. Funct means whatever you're going to do, meaning it's an opcode also. Okay, we're going to look at that later on. Okay, with operate instructions such as addition, we tell the computer to execute arithmetic or logic computations in the ALU. We already said that actually. But we also need instructions to access the operands from memory. If everything was in registers, you don't need anything to access memory with. But registers are small. You need actually large amounts of memory for storing data. So we need to load data from memory to registers, and we need to store data from registers to memory. And we need instructions to do that. And so far, we have not looked at that yet. So we're going to see that soon. How to read or load from memory. Writing is performed in a similar way, but we will talk about that later. Writing is exactly opposite action. So let's take a look at load word. This is high-level code. This is an array operation. You have an array at base address A, and I is the ith element in the array. How many people have programmed with things like this? Okay, good. How many people have not programmed with things like this? Okay, good. I'm not surprised. you should have programmed with things like this. So you're basically accessing ith element in this array. And then I'm assuming the array is stored in memory, assuming it's a huge array, right? Later, we will see models where things can be stored in registers like GPUs. So some folks ask questions about the GPU execution model. Wait until lecture 16 or so, or later actually, even later. Okay, so this is the assembly. The destination is a variable, A. I'm going to have a base address A and an index I. And this assembly says, load from that base address, calculate an address into the actual location indexed into this array from this base address, get the data from there, put it into variable A. And we're going to map the variable to a register. Load is a mnemonic to indicate the load word operation. And in this case, it's a load word, meaning get a value of size word, 32 bits in MIPS. A is the base address, I is the offset. This is also called an immediate or literal. Essentially, it's a constant. A is the destination operand, destination variable. And the semantics looks like this. I already said this basically. Okay, so let's take a look at how this is encoded in LC3 and MIPS. LC3 assembly looks like this. In this case, index is 2. And this is the assembly. We have a load register, LDR, opcode. this is a register 0 stores a base address A, and number 2 is encoded in the instruction. This is a constant encoded in the instruction specifying what is the index, and this is destination register. Okay, and this is the semantics basically. You take the value in R0, which is hopefully A, add 2 to it, calculate the address, go to memory, get the data, place the data into register 3. Okay, so if you look at MIPS assembly, it's going to be very similar essentially. The same code, the same high-level code, translate into a load word instruction. It's the syntax is a little bit different, but it's essentially the same thing, right? What we do is this: the base address is in S0. We get the value over there, add to it 2, and access memory, get the data, put the result into destination register S3. Okay, this is assuming that MIPS is word addressable. I'm going to look at a byte addressable version of it. We're going to multiply that 2 by 4 basically. That's what's going to happen because if you're byte addressable, your word is essentially each element, assuming your elements are word sized, each element is 4 bytes, right? Okay, so these instructions actually happen to use a particular addressing mode. We're going to study addressing modes later today or tomorrow. The way the address is calculated, addressing mode is also specified by the instruction set architecture. It tells you how do you calculate the address. In this case, we calculate the address using an addressing mode called base plus offset. We have a base register and we add an offset to it. And the offset happens to be an immediate, meaning a constant specified in the instruction. Okay, now let's take a look at load word and byte addressable MIPS. This is high-level code. No, there's some sound coming. Okay, so basically MIPS assembly of this code is assuming you have word-sized element in this array and your memory is byte addressable. In order to access element 2, you need to multiply the offset by 4, right? 2 times 4 is 8, so my offset is going to be 8 over here. And that's how I access the second word in a byte addressable memory. Basically, byte address is calculated as word address times bytes divided by word. Bytes divided word by word, bytes in a word in MIPS is 4. And we already discussed that. If LC3 were byte addressable, you have 2 bytes per word, and you would multiply it by 2 essentially. And you will see that later on. Okay, now let's encode these. These are the instruction formats with immediate for LC3 and MIPS. As you can see, they look very similar. I look at the byte addressable version of MIPS because MIPS is really byte addressable. That's how the ISA is defined. LC3 is word addressable. That's how the ISA is defined. Okay, and these are the field values. Now you can see this is a different kind of format. Opcode in LC3 is 6, specifies LDR. Destination register is 3, base register is 0, and there is a 6-bit offset field over here. With a 6-bit offset field, you can easily encode 2, right? And you get 2 over here. Right? So this is the encoding, basically. We use all of the bits over here. In MIPS, it looks like this. You have the opcode. It happens to be 35. You don't have funct. Because opcode looks like this, the rest of the instruction looks like this, meaning you have a source register, you have a destination register, so S0 happens to be 16, S3 happens to be 19 in MIPS encoding, and immediate is huge, 16 bits as you can see, and that's 8. So basically, this is the encoding of this instruction. It's called an I-type, immediate type instruction, which means that it has a 16-bit immediate value. Half of the instruction is dedicated to encoding a constant value. Does that make sense? Okay, we're going to see more of these soon. We're just studying the encoding right now. Okay, so hopefully this gives you an idea of how instructions are encoded. We're going to see more of these encodings. But before we do that, let's see how these instructions are processed a little bit, because we're going to tie the encoding to the processing also soon. Okay, we're going to introduce the instruction processing cycle or instruction cycle. This is not to be confused with the clock cycle. It has nothing to do with the clock cycle. It's really how the instructions are processed in the machine. So basically, how are these instructions that we encoded get executed? Now we can speak the language of the computer because we encoded things in a way the computer can understand, and the computer can decode them using a lot of decoders, which you have seen. So we know how to tell the computer to do things, like execute computations in the ALU by using, for instance, an addition instruction. Access operands from memory by using the load word instruction. But how do these get executed on the computer? So the process of executing an instruction is called an instruction cycle or instruction processing cycle. I like the second one better, instruction processing cycle, because you're really processing instruction. It's called a cycle because you keep doing this repeatedly. Okay, so basically every instruction goes through a sequence of steps or phases to be executed. And these are the general cases: fetch, decode, evaluate address, fetch, operands, execute, store result. These phases may not be needed in every instruction. Not all instructions require all the 6 phases. Every instruction needs to be fetched. You have a program counter, you need to fetch the instruction, you get the data bits of the instruction, and then you need to decode the instruction to figure out what the instruction is telling the machine to do. And then you need to evaluate the address so that you get the operands, and then you fetch the operands, you execute the instruction by doing something to the operands, and then you store the result. But not all instructions require everything. For example, load register does not require execute, right? You fetch the operands, you fetch the operand from memory, and put it into a register, destination register. There's no operation that you do, really, in the ALU for that, as you will see later on. Add doesn't require evaluating a memory address. In this case, evaluate address implicitly means memory address. You don't have, at least in LC3 and MIPS, you don't have add instructions that directly operate on memory. All of them operate on registers. Okay? This is good to keep in mind. It's also good to keep in mind that this is not the case in every single ISA in the world. People have imagined many different things. x86, for example, has instructions, operate instructions like add, that operate on memory values, register values. You can, in x86, you can specify, I want to add this memory, add the data value in this memory location to this register and store the value in some other memory location. Okay? This enables you better expressibility. You don't have to do things only in registers and then put the value into memory. You can directly operate in the memory locations without bringing the data into the registers. And there could be value to this, as we will see in later lectures. But we're not going to see ISAs, and you're not going to implement ISAs like this in your labs, for example. But this is an example instruction in x86 that says, get this, EAX is a register. You use it as an address. You access the memory location, get the data value in that memory location, add to it the value in the EDX register, and then store the result into the memory location that's addressed by EAX again. Okay? So source and destination are the same in this case. Again, you don't need to understand this, but there's no one single way of doing this. And the benefit of doing operations directly on the memory locations is you don't need to waste registers. For example, you just need to add something to somewhere in memory. You don't need that value again. Remember, registers are very small, precious. You want to keep things that are being used over and over inside your register file, but you just want to increment some random location in memory because you're keeping count somewhere once in a blue moon. Just do it in memory. Don't bring it into a register, right? So there are good reasons why people add these things into the ISAs, but they do complicate the ISA also. They do complicate the implementation in the end. Okay, so after you store the result, an if fetch happens. Basically, that's why this is called a cycle. Now we're going to go through each of these stages. Does that sound like fun? Okay, you're already having fun, I can tell. Okay, so fetch phase. So this phase obtains the instruction from memory and loads into the instruction register. I kind of said that actually earlier, but every instruction has to go through this. The complete description looks like this actually. I'm going to show you a picture also. You load the memory address register with the contents of the program counter, which is the address of the instruction, as you know, and simultaneously increment the program counter because you're going to go to the next instruction later at some point. And then you access memory or interrogate memory as used by Pat and Patel. Memory returns the results into the MDR. Basically, by interrogating memory, what the memory does is it takes the address in memory address register, accesses itself, and puts the data into the MDR. What is data? These are the contents of the instruction, right? Because we're accessing memory with the program counter. Okay. And then you take the data that's put into the MDR by memory data register, put it into the instruction register. Does that make sense? So there are 3 steps to get the contents pointed to by the program counter, which is the address of the instruction that you want. Eventually, after these 3 steps, the instruction that you want at that program counter, at that memory location, gets placed into the instruction register. Now you have the full content of the instruction. You fetched the instruction. What we have done, in other words, is we have interpreted the address, the program counter, as the address of an instruction, because we're accessing memory in the fetch stage. Now we're accessing memory using the program counter in the fetch stage, putting the data that's coming out of the memory into the instruction register. We're interpreting the data at that location as an instruction, right? Okay, this is going to be hopefully clear later on because we're going to access memory in some other stage also. We're not going to put the data into the instruction register. Just because we're in the fetch stage of execution, the control unit is putting the data value coming out of memory into the instruction register. So we're treating that data value in memory as an instruction. Okay. Okay, let's take a look at how this is done in this high-level picture, microarchitecture of LC3. So step one, you load MAR and increment the program counter. What do you load the MAR with? You basically take the program counter. So there's some program counter over here. There needs to be control signals set accordingly in this stage. So there needs to be a finite state machine controlling this, as we will see also soon. The finite state machine says, I'm fetching the instruction, I'm in the fetch phase. So I'd better set the gate PC signal to enabled so that the value on the PC gets gated onto the bus. Remember the tri-state buffer? That value flows on the bus, and I'd better set the enable signal or load MAR signal to be 1 so that whatever flows on the bus gets placed, written into the MAR register. Load MAR means write enable. It's essentially a write enable signal for MAR. So now we've kind of put together all of the concepts that we've seen earlier. We have a register, PC, we're gating it, its value, using a tri-state buffer onto this wire bus. And then we're write enabling the register where we want the address to be placed into MAR. That could take 1 clock cycle, okay? Don't worry about clock cycles right now, but these are steps. Okay, and then there's another step where we access memory, and at some point, accessing memory happens by, it basically takes the address in the MAR, which is essentially the program counter's value, accesses itself using the decoder, all of those bits, multiplexers at the end, and the data that you need eventually comes out in the MDR, the word, the instruction word. Of course, you need to set the load MDR signal to be 1 so that this MDR gets written into. The third step is, once that is done, you load the instruction register, which happens to be over here, with the content of the MDR. To be able to do that, we need to have a path from MDR to IR, and that path already exists. And the finite state machine, so you can think of these as 3 different states in finite state machine. State 1, state 2, state 3. Finite state machine in this state enables MDR signal, gate MDR signal to be 1, such that the value in MDR goes onto this large bus that we call the processor bus. It also write enables the instruction register, or load IR as it's said in this book, such that the data value that's coming out of this processor bus gets written into the instruction register. Okay? So now, hopefully, you kind of connected the dots. Everything we have seen previously enabled what we have done over here. We're now able to fetch an instruction using both sequential and combinational logic and a finite state machine that I didn't show you, but you could imagine that finite state machine. I'm going to show you that later on. In one state, you do this, and then you move to the next state. In the next state, you do this, and once the memory says, I'm done, you move to the next state. In the next state, the finite state machine does this. So after 3 states, you get the instruction that you want, okay? So all of this is done using sequential and combinational logic together. But of course, you needed to design the machine to do that also. Sounds good? Okay, so that was fetch. We're going to see more of this later on. Let's talk about decode. Now you fetch the instruction. The contents are in the instruction register. The decode phase does what decode means. We decode the instruction, identify what the instruction is, and what we should do afterwards, right? It also generates, essentially, what we should do afterwards means it generates a set of control signals to process the identified instruction in later phases of the instruction cycle. Basically, it determines your next states in the finite state machine. If it's an add, I execute the sequence of states. If it's a multiply, I execute this other sequence of states. If it's a load, I execute this other sequence of states in the finite state machine, right? Okay, we're going to see that finite state machine. So basically, we're going to use a decoder. So in this case, we have 4 bits opcode in LC3, and a 4 to 16 decoder identifies which of the 16 opcodes is going to be processed. So the input is 4 bits, the top 4 bits of the instruction register, because we've already fetched the instruction from memory, and the remaining 12 bits identify what else is needed to process the instruction based on those 4 bits. Okay, so let's take a look at decode. We're not going to see a whole lot here, but basically, we identify the instruction to be processed. Essentially, the top 4 bits of the instruction register goes through a decoder, and essentially affects this finite state machine that we're going to see later. It also generates a set of control signals to process the instruction later. For example, it says, oh, I should go through these states next. We're going to see this more. But that's decode, actually. Identifying the instruction and generating the control signals for what should happen next in the future because I have fetched this instruction. Right. Okay, fetched and decoded. So you can see there are a lot of control signals over here. We will demystify this picture later. I don't want to go into a lot of microarchitectural detail right now, but you will see a lot of this later. And you'll see different kinds of control logic. Okay, decoder, hopefully you remember. Again, there's no magic over here. A 4 to 16 decoder identifies what instruction you're executing. And remember, I said that the input pattern could be the instruction in the program, and the processor needs to decide what action to take based on the instruction opcode. Hopefully now it's much more clean. So this is the full finite state machine. I don't want to scare you, but this is LC3B actually, which is byte addressable. It makes things slightly more complicated. You can find this online. We should also upload it into Spring 2025 website if you haven't done so. But just to show you these stages that we talked about, this is the fetch phase. If your finite state machine is here, what you do is you generate the control signal such that PC gets loaded into memory address registers, and concurrently, I forgot to say this in the picture, sorry, concurrently you increment the PC by 2, because you're going to go to the next instruction later at some point, right? You could do this later also somewhere, but they decided to do it in this state. And then unconditionally, you jump to next state. Remember, in finite state machines, we have the next state logic. After 1 clock cycle, unconditionally, you go to the next state, okay? The unconditional, and the next state, memory uses the memory address register to access data from itself and places the data into the memory data register and stays in the state until the ready signal is asserted. If the memory is not ready, meaning memory access may take a long time, it's actually an analog process, as we will see later on, analog plus digital process. Memory asserts a ready signal once the data is placed into the MDR. And you go to the next state only when memory does that. And the next state, memory data register gets loaded into the instruction register. So this is our fetch phase. And this finite state machine controls all of those operations, as you can see. Again, there's no magic. We've seen finite state machines. We've seen logic. This is the controller that we have. Next phase is decode. Now, what's happening over here is, again, unconditionally, you go to the decode stage. There's some stuff that we're not going to talk about right now, but based on IR 1512 over here, you decide where to go in the finite state machine. The next state is determined by the opcode, right? And each of those opcodes have a different thing to do. For example, if the opcode is add, in the next state, you do this. You add SR1 to SR2, store the result in DR. And then you go to state 18, which happens to be the fetch phase. Right, so you go to the next instruction, basically. And you've already incremented the PC, you fetch the next instruction. Does that make sense? So this is the operation of an entire LC3B machine, which is a simple machine. Existing machines you can specify as, so a processor over here, it is also a finite state machine. It's a much more complicated finite state machine, but it is a finite state machine. Okay? Okay, so that hopefully is clear. The next phase in execution is evaluate address phase. This computes the address of the memory location that is needed to process the instruction. So this phase is necessary in LDR because it requires access to memory, and you need to evaluate the address that you need to access. So in LDR, you need to compute the address of the data word that is to be read from memory by adding an offset to the content of a register, if you remember, base plus offset addressing mode. This is not necessary in add, so add doesn't have a state in the finite state machine for this. So if you look at the finite state machine, add doesn't evaluate address. It just takes SR1, SR2, does something. Right? Whereas LDR, this is testing my eyes. Now, well, this is LC3B, so there's an LDW, which is same as LDR. It does some address evaluation. This is the evaluate address state. Okay? Okay. So not necessarily NAT. So let's take a look at this in the microarchitecture. LDR calculates the address by adding a register and an immediate to each other. This is a specification if you look at this. You have a base register and you have a sign extended offset. We're going to see this later more and more. But basically, you need to take the register value in this state from one of the registers, and then you need to add to it the bottom part, bottom 6 bits, coming from the instruction register, and you need to put that into the MAR, okay? So that you can access memory. Now we're going to access memory with that. So I've added that adder because you needed it in this particular case. It'll become more and more complicated, that adder. We will see that in the next lecture. But this is not magic again. You can imagine building this, and it's not that hard to build. Okay, let's talk about fetch operands. Fetch operands phase obtains the source operands needed to process the instruction. In LDR, now we've calculated the address. You put the, you load the MAR with the address calculated in the evaluate address stage. You read the memory, which places the source operand in the memory data register. In add, you obtain the source operands from the register file. In some microprocessors, operand fetch from register file can be done at the same time you're decoding the instruction. That's also possible. LC3 microarchitecture that's discussed in Pat and Patel doesn't do that, but we're going to see that later on also. When we build pipeline processors or when we build one of our MIPS processors, you will see that. Okay, let's take a look at fetch operands quickly. In LDR again, the step one is you take the, you load MAR with the address we calculated earlier. Let me just jog your memory. We calculate the address over here. That address needs to get into the MAR. So in the finite state machine, you need to set the control signal load MAR to be 1 so that the address that you calculated gets loaded over here. And then you do the memory access, which is very similar to the fetch stage, except it's a different state because now we're treating memory as a source of data that will be used as an operand as opposed to as a source of instruction that will be placed into the instruction register, right? Okay, so now the data comes to MDR, and that will be placed somewhere later on, but we'll talk about that. Execute phase executes the instruction. In add, it performs addition in the ALU. In XOR, it performs bitwise XOR in the ALU, etc. It happens basically add, let's take a look at add. Adds SR1 and SR2. In this state, you set the control signal such that you access the register file. The data comes through the ALU, so you have SR1, SR2. There are some control signals that make sure that both of these registers go to the inputs of the ALU, and the ALU operation is add. These are all control signals, and the data comes, the result comes out of the ALU. That needs to be gated, meaning this tri-state buffer called gate ALU should be enabled such that the result gets put onto this wire processor bus, and later in the next phase, it's going to get stored into the register file. Make sense? I'm kind of breaking the phase, but these may actually be completed in a single cycle. These phases have nothing to do with clock cycles, as I said earlier. Multiple phases can be collapsed into a single clock cycle. A single phase can take many clock cycles. Like fetch itself takes at least 3 clock cycles, right? But here, execute and store result actually happens in the same clock cycle for add instructions. Okay, store result. This phase writes the result to the designated destination. So once store result is completed, a new instruction cycle starts with the fetch phase. So let's take a look at store result. Add loads the ALU result into DR. So ALU result was gated onto the processor bus. Oh. And then you need to set the control signal such that you write enable the destination register, and you have the destination register ID coming from the instruction register based on the encoding, if you remember. So there's no magic again. The destination register ID is encoded in the instruction register and it gets connected to the register file, and the register file gets write enabled such that you write this data that's coming off the processor bus into the register specified by the instruction. Okay? LDR, if you do LDR, you load the data that was placed into the MDR, memory data register, and set the control signals such that you gate the memory data register tri-state buffer and a memory data register gets on this processor bus, and you set the destination register, load register signal accordingly, such that you write enable the register file, and destination register comes from the instruction register, instruction bits over here. So you need to set the control signals accordingly such that MDR gets into destination register. We're going to see different ways of doing that later on. But now I've given you a complete instruction cycle for multiple types of instructions. Different instructions do different things clearly. We've looked at add and load. Hopefully this makes sense. We're going to see more and more of this. Okay, how much time do we have? Let's see. No, we can change the sequence of execution. There's enough time. Because it's important, you need to change the sequence of execution, and then there'll be a clean state. So we've seen a couple of examples of instructions. What we have not seen is this. Normally, we execute instructions in program order, sequential order. First instruction, second instruction, third instruction. You keep incrementing the program counter. Unless we can change the sequence of execution. So control instructions allow us to do this. They allow a program to execute out of sequence. They can change the program counter by loading it during the execute phase. Meaning there are instructions that operate directly on the program counter. Program counter is an architecturally visible register to the programmer. Programmer can say, I'm going to put value X into the program counter, which means that the next instruction that I'm going to execute is going to be at address X, right? So you're very powerful as a programmer, as you can see. The program doesn't need to be executing in sequence. So basically that wipes out the incremented PC that's loaded during the fetch phase and loads the incremented PC, loads whatever you're loading after the execute phase. So let's take a look at an example. Unconditional branch or jump in LC3. It looks like this, jump R2. R2 is the register. And what this does is, this is the encoding. You have a base register has a value. Basically, program counter gets the value in the base register. Makes sense, right? Whatever value you put over there. So you can jump to anywhere in memory. Any place in memory can be construed and interpreted as an instruction. So you could have instructions all over the place. This is the register addressing mode, as we will define later on. There are variations of this. There's a return. This is a special case of jump where base registers are 7. You can do function calls. This is how you can jump to a function, for example. You have a base register, you jump to a function, and then you can return. These are jump to subroutine. This is actually how you really jump to a function that you will see later on. And then there's a jump register also. Okay. So there's a jump in MIPS. This is unconditional branch or jump. It looks like this actually. In MIPS, it's a little bit different if you look over here. This is the opcode 2. Opcode is the top 6 bits, and the rest is the target. So how do you use that target? This is called the J-type instruction MIPS. Somebody defined it this way. Not my fault. It's somebody else's definition. Target address is essentially the target address, essentially where you want to jump. But this is how the full program counter is computed. You basically take the incremented PC, top 4 bits of the incremented PC, concatenate to it these 26 bits multiplied by 4. Why this target is byte addressable? You multiply it by 4 because instructions are word aligned. They're actually words. So you multiply it, this by 4 so that you can get the word address. And you concatenate to it the top 4 bits of the PC. This way you can jump relative to the program counter. Your program counter is here. You use the top 4 bits. They don't change. But relative to it, you find a location to jump to, right? It could be anywhere within the vicinity of 2 to the 26 up there and 2 to the 26 down there. You or take some -1s. Okay, this uses a pseudo-direct addressing mode. We will see this later on. It's also called a PC relative addressing mode. So there are variations like jump and link function calls that I'm not going to talk about. Okay, let me just show you and then we'll be done. So how do you update the PC? Jump, for example, loads SR1 into PC. There is a path from register file that goes through a multiplexer, and you can actually set the load PC signal over here. That way you can put a register into the program counter. Okay, this is where I'll stop. This is where we will pick up. Hopefully we will go into more instructions and look at trade-offs in the ISA. I'll see you tomorrow.
usually